All right. All right. So now we are going to finish our discussion on surfaces um, by talking about surface to surface contact. And really, we're talking about surface to surface contact area and pressure. This study is commonly referred to as Hertzian contact or Hertzian stress, and it's the study of two surfaces in contact with one another. Now, if we take a look at two, say, perfect spheres, okay, so if this is a sphere and then we have another, imagine my drawings are perfect spheres. So if we have two perfect spheres and we take a look at this point right here, let me get a higher contrast pen. So let's say we look at this contact right here. Well, actually, if these are both perfect spheres and they're both perfect and they're non-compliant, then at that point where these two are contact, goodness gracious, at the point where they're contacting, right there, really that contacts, this is a point contact. And at a point, we basically have, at a perfect point, we would have zero area. So if we divide the force, of contact, F, over that area, and the area is theoretically a point, then the area is really, really small. And then that means that if the area is almost zero, then the stress is almost infinite. So obviously, if we look at, say, if we're talking about the contact between two surfaces, and let's just say we have a situation like this, and we have this surface A, and we have this surface B, and it has this really sharp point on it. And if we take a look at its cross-sectional area, okay, we look at this A, well, A is much less than 1. Let's say it's really, really small. So if we have a load between these two surfaces, obviously that load's going to go across that area. And if you think about that in terms of the axial load, the axial stress, the force over the area, and if you look at the stress strain diagram for some material, then it doesn't take a whole lot of force to get a lot of stress, which gets us past our proportional limit and into plastic deformation, and then this material deforms. So when you have surface-to-surface contact, where those surfaces contact, if you have a sphere, okay, they contact, say, at a point. And then if you have the contact between two cylinders, you would have a line of contact. Okay, so your line of contact for two cylinders would be here, and if you have two perfect spheres, then you would have point contact. So obviously, because of this phenomenon over here, when you have these pressures between surfaces, you actually get enough force to compress the material, and the material compresses enough so that you actually get increased contact. And so what Hertz did when he was 24 years old is he was studying lens is. Okay, so this is what a lens might look like that would, say bend light. And this is a convex lens, and he studied what happened between, a lens, when it was on a surface and subject to a load. So it turns out that if you zoom in here, you get, instead of this elliptical path that would, theoretically contact at a point, you get contact that's spread out over some distance, and in fact it looks something like this in terms of its contact with the surface. And so that contact here, due to that load, we call the contact length. So it, forgot the Z in Hertz's name. Okay, and this is the same Hertz that proved electromagnetic wave existence, and he's also the same guy that we name the unit of frequency, the Hertz, which is 1/seconds, is also attributed to him. Now, if you look at this, this type of contact shows up in a lot of different places. Okay, so if you have rolling contacts between surfaces, you have roller bearings, or you have needle bearings. Obviously, they show up quite a bit. Or if you have, say, a ball on a plane, which would be like a rail car or other type of rolling applications, it shows up everywhere. There's a lot of work that's been done on this. What we're going to talk about here is a basic understanding, and this basic understanding will be sufficient for us to understand some of the design features, but just know that there's a lot more information out there than what we're going to describe in this section. Okay, so for Hertzian contact, we're going to look at two cases in this class. We're going to look at the sphere on sphere that has a load. Okay, and this load is F, and this sphere has radius 1, and it has properties Young's modulus 1 and Poisson ratio 1. And this material here has radius 2, and it has Young's modulus and Poisson ratio associated with that material. And it turns out that if you take a look at the actual stress distribution or the pressure distribution between surfaces, you have a profile that looks sort of like this on the material, and in the center you have a max pressure on that surface, and that max we call P naught. Okay, so P naught is the max pressure, and this max pressure is also the stress in the z direction. And so these are the important parameters, the two radius for the two balls. And if we can also extend the second one, and if R is an infinite, so if R2 is, or the second surface is a plane, then R2 is infinite in the case of a plane. If you have a cylinder inside a convex surface, okay, then in this case R2 is actually negative. Okay, so we also take a look at two cylinders in contact with each other. Okay, and in the cylinder to cylinder contact, okay, what we look at is the length of contact, Okay, and we're going to look at this profile. So the pressure profile looks like this. If we're considering 1, that profile is over the length, and it also has a max pressure P naught. Okay, so the pressure profile for 2 cylinders looks like half of a cylinder. The pressure profile for the 2 spheres looks like half of a sphere. This distance over here between the edge of the pressure profile and the center of the profile, that distance we call B. And I'll show you in a minute that the distance from that pressure profile to the edge of where it affects, we can actually get some standard expressions for the stresses as a function of that difference. All right, and so in the case of the 2 cylinders, what Hertz effectively contributed was what he called a contact modulus, and in your book it calls it delta. And this contact modulus is related to the Poisson ratio, mu, and the Young's modulus for each material. Okay, in the case of cylinders. So we have 1 minus mu1 squared over E1, and then 1 minus mu2 squared over E2, and that gives us our contact modulus between those 2 different materials. And for the 2 spheres, we can calculate the max pressure as 0.578 times the force between the 2 different surfaces times 1 over R1 plus 1 over R2, and this is quantity squared, and that is divided by the contact modulus squared, and this is raised to the 1/3 power, or the cube root of that. And this is our max contact pressure, P naught, and it's also equal to our stress in the z direction. And from that we can look at the length A. Okay, and A is the, if we took this little dome here, okay, from the contact pressure, we have this contact pressure profile, and this is a circle, should be a circle down here. Forgive my drawing. So we have this contact pressure, goodness gracious, let's try that one more time. So we have this parabolic contact pressure, and then on the bottom we have this circle, and it kind of looks like this, and this peak pressure is in the middle. Okay, this is our P naught. All right, and this distance here, the radius of this is A. Okay, so that's A. A is the radius of that contact circle of those pressures. Okay, in this case it's A. That's the parameter that we have that we can look at. And in this case over here it's B, and that's the distance to the edge. And so we can calculate the contact max pressure using the contact modulus, and also using the contact modulus we can calculate that parameter A, which is the contact radius, and that is 0.908 times F times delta over 1 over R1 plus 1 over R2, and that's also to the 1/3 power or cubed root. We have another expression as well for the two parallel cylinders, and that expression is for P naught, and that's the max pressure at the middle of this pressure profile, and it is 0.564 times the square root of F times 1 over R1 plus 1 over R2 divided by the length of contact, that's this L here. So that's this length of contact from, here to here. That's L. Times delta, quantity square root, and we can calculate the contact length B as 1.13 times the square root of F times delta divided by the contact length times 1 over R1 plus 1 over R2. And as I said before, these are by no means all of the contact surface scenarios that you get, and there's a more in-depth treatment in some other books, but it's sufficient for just kind of taking a look at how surfaces contact one another. Okay, so obviously this is important when we talk about gears and we talk about rolling elements on surfaces. So in this approach, there's a couple of assumptions to this Hertzian contact that we need to mention, and the assumptions are that we have frictionless contact, which we know is not true. We have perfectly smooth surfaces, which we also know is not true. We have perfectly isotropic materials, which is also not true, which means their properties are the same in all directions. And we have perfectly homogeneous materials over all the contact distance, which we know is not perfectly true. And we are assuming that both R1 and R2, the contact radiuses of both the balls and the cylinders, are much greater than A in the case of spheres, or B in the case of cylinders, or we could just say they're much greater than A or B. Turns out that this approach is useful and gives us reasonable numbers for the max pressure, and so we use it. So this gives reasonable numbers for our max pressure, which is equal to our stress in the z direction, which we can use for design. Okay, so this is useful. Now, what we need to take a look at here is to take a look at how the pressures look. Pressures at a distance below the surface. Okay, and if we take a look at that, we actually have a couple graphs, and these are taken from your book, and they show us what it is. Now, also, I want to show you there's a picture of the contact stresses. Okay, So this is photoelastic measurement of contact stress. Okay, this is due to the change in optical properties of a dielectric material as a function of its strain tensor, but it shows how the stresses develop at a depth in a surface. And so this would be like a cam and follower or roller on surface, or etc. There's another image here just showing the photoelastic stress from a dielectric, and a lot of plastics aren't just simple dielectrics. All right, so I wanted to show you this, and this is the stress. This is taken from your textbook, and it's the stress that develops at a depth in terms of the max pressure that can be calculated with the Hertzian stress. Okay, so P naught is that value that we calculate. This is for the two spheres, and A is that contact radius that we discovered. And for the sphere-on-sphere contact, because of symmetry, your stresses in x and y directions are the same. Your stress in the z direction is the same as the max contact stress. Okay, so that's in the center of that contact region. We say that it's negative because it's a compressive stress in that material. And then we can relate these values and also get our max shear using Moore's circle, because that will be the radius of that circle for that state of stress. And on the y-axis, this is the distance below the surface as a function of the parameter A, which is that contact radius. So at the depth of the contact radius, we're almost at 50% of the stress, and the stresses in the x and y direction are almost zero. Now, if we take a look at the cylinder-to-cylinder contact, we have this stress distribution, and because we have different geometry, we don't have symmetry in the x and y directions, then x is not equal to y except for at one point where they cross over. The stress in the z direction is equal to the max stress between those cylinder-on-cylinder contacts. And then we look at the depth as a function of the contact length, half the contact length of the cylinder to cylinder, which is that B parameter that we calculate using the Hertzian values. And so what's kind of interesting here is we have this shear stress profile that actually has non-zero value due to the applied stress initially, and it goes down and actually peaks out over here. Okay, so it's something to watch out for in terms of failure. So another thing that is interesting to look at is I have to move this up a little bit so you can see it. And that is how the stress between cylinders develops. And when you have the cylinder-cylinder contact, you have the max compressive stress, which is sigma z, and it's about 70% of the pressure. 10% of the pressure is going to be your sigma y, and then 25% of that pressure is sigma z. And this is at a distance b below the surface. Okay, so if you look at this distance b here, that's that distance b, that's that peak. It's almost that peak stress below the surface. And so at this point, you actually get your highest shear stress, okay, which is about 30% of your applied downward pressure. Okay, so from a design perspective, this is pretty useful to understand this type of contact and to understand the relationship between the max shear that develops in a material. And this all comes out of the Hertzian contact theory. So what we also want to discuss before we leave this study of contact between surfaces is rolling contact. And this type of contact is very important in a number of machine applications and is a predominant reason for fatigue. Okay, so if we take a look at the rolling contact between two spheres, even though they don't perfectly look like spheres, we're going to call them spheres, and we have a downward force or between the materials, and if we have if these are rolling, okay, so let's say that this is rolling and we have rolling contact, then if we take a look at that location, at that distance B, okay, on either side, this is our distance B, and what we have is a state of reversed shear, okay, and so from this guy over here we have this type of shear, and then over here we have this type of shear, and so we have this shear stress, okay, which shows up on these elements, and we just talked about where that shear stress occurs at that distance B below the surface, okay, and so this state of stress at this component A and this component B is reversed shear. So as an element is making its way, it's going to go from a state of shear at A that looks like this over to a state of shear at B that looks like this. And in addition to the shear stresses, we also have, as indicated in the graph previously, we have the excuse me, we also have the compressive stresses here in X and Y that show up. I know this is getting a little bit noisy, so I'm going to redraw over here. So if we look at element B, okay, actually get the state of shear. So we have element B, and then element B, we have this max shear that happens because we're at a distance B below the surface. But we also have these compressive stresses that also show up. And A will look just like this, except it'll look as though it's reflective, and so we basically go from this state of shear to the opposite state of shear and have fully reversed shear. And instead of calling this tau xy, I'm going to call this tau max to be consistent with that graph. If we look at it, the pressure okay. So this mechanism of reversed shear is in a rolling component causes repeated loading of the elements as they rotate around, and this causes cracks both on and below the surface, okay, and is related to the fatigue uh, wear of a component, or what we call surface fatigue. Okay, so when we look at this component over here, what we have is we have a stress that looks like this, stress that looks like this, okay, and this is at a distance of 2b below the surface, and it occurs at minus b and b in the surface. If this is our pressure P, and this is about 0.3 P naught, that max pressure occurs, and this mechanism of loading and unloading of these elements causes this surface fatigue, and this causes two mechanisms. That's called pitting and spalling. Okay, pitting originates with surface cracks and is usually over a small area. If you've ever seen like a pitted surface on a bearing, and I'll show you a picture in a second. Spalling originates below the surface and creates spalls, which are thin flakes of material, and they'll come off the surface and get stuck on the surface. And this is a common failure for gears. This is a common failure mode for gears. Both roller elements, or roller bearings, ball bearings, needle bearings, cams and followers, and wheels on rails. Let me show you what those look like. So here's an image of what spalling looks like. That's the subsurface damage. So those stresses cause cracks underneath the surface to occur, and then the flakes of material will, or the spalls will come off. And then pitting is where we have cracks that initiate on the surface due to those high stresses and cause them to come off. All right, so let's do an example of how we might calculate these. All right, so if we say we have an example, say we have a 1-inch steel ball on a plate loaded with 100 pounds. Okay, so we have our steel ball plate we have a load of 100 pounds. And we have R1, excuse me, R1 is 0.5 inches, and then R2, okay, so this is a plane, so R2 is infinite. We have the Young's modulus of the first material, which is steel, is equal to the Young's modulus of the second material, because it's a steel plate. And that's 30 times 10 to the 6 psi. We have our Poisson ratio for the first material, which is steel, which is equal to the Poisson ratio for the second material, which is 0.3. We have R1 is 0.5 inches, and R2 is infinity. So the question is, find the pressure and contact radius between surfaces. Okay, and so we can go into our theory and we can find our contact modulus. Okay, and in this case we use the contact modulus between spheres, and we treat this as a sphere with an infinite radius. And our effective contact modulus from the equations is 1 minus u1 squared over e1 plus 1 minus u2 squared over e2. But since they're the same, we can just say it's 2 times 1 minus 0.3 squared over 30 times 10 to the 6, which is 6.07 times 10 to the minus 8. These should come out as small numbers. And then from that we can calculate our pressure, 0.578 times the load of 100 times 1 over the first radius minus 1 over the second radius. 1 over infinity is 0. Quantity squared over the contact modulus squared to the 1/3 power, and that gives us 275,733 psi, and we can calculate the contact radius between the surfaces. It's 0.908 times our load times our contact modulus, and that is divided by 1 over our radius for one plus 1 over radius of the other, which is infinity, to the 1/3 power, which is equal to 0.013 inches. Okay, so it's pretty interesting that we can calculate these and get a feel of, what is that downward stress, sigma z, and we can relate that then to our material properties and make sure that where we need to be. If this is going to be for an application where this is cyclically loaded, then we could use our fatigue analysis to find out the life. But this is a way where we can actually get real numbers that we can use for design. Alright, so in conclusion, wear in the study of surfaces is a big deal. In fact, wear accounts for about or greater than 1 trillion USD, okay, and that value is extrapolated. Sorry about that writing here. Extrapolated is what that word should be, from a 1978 study in a CE report. Okay, now that's a big deal. That's a big number, and when we design machines, ideally they would last forever. We'd be able to recycle them, and we'd have no problem. Obviously, we know what happens to old equipment when it's left outside, or old farmhouses where you have a bunch of old tools in there, and that things wear out. But wear is something, it's a design problem. Okay, so as a designer, you can design for wear. Okay, you can design for things to be replaced. You can reduce wear by making surfaces smooth. Okay, so you can pick a different process for the manufacturing, or you can post-process it. Obviously, there's an optimization in cost, but smoother surfaces have less wear. You can make surfaces harder. Harder surfaces have less wear. You can increase residual compressive stresses. Okay, so this is why we use shot peening, for example. And residual compressive stresses increase the life of components. You can choose the best materials. Okay, and we're not necessarily talking about the best in terms of the most expensive or whatever. It's just saying you can make a decision against wear with the decisions you have against material. You can coat materials to extend the life, and there's so many options. Okay. Okay, you can extend the life of the material, so so many options, and as an environmental concern, you can avoid using toxic materials that will inevitably wear into the environment. Something you have to be concerned about. So that concludes our discussion of surfaces and wear.